The device you're watching this on right now, the lights in your room? Yeah, our entire modern world, it runs on a single, almost magical discovery, a hidden link between magnetism and electricity. So today, we're going to dive into the story of the spark that literally powered our planet.
For the longest time, you gotta understand, these two forces were complete strangers. Magnetism, that was for compasses. Electricity, that was the weird static shock you got from rubbing stuff together. As far as anyone knew, they lived in totally different worlds. That was the thinking, way back in the early 19th century.
But then, a few scientists, guys like Ørsted and Ampere, they found the first real clue. They discovered that an electric current, just electricity flowing through a wire, actually creates its own magnetic field around it. A field strong enough to make a compass needle move. So, electricity could create magnetism.
And that, right there, became the big question, the multi-million-dollar question of the day. If electricity can make a magnet, can a magnet make electricity? With no battery, no nothing? Around 1830, two brilliant minds, Michael Faraday over in England and Joseph Henry in the US, were basically in a race to find the answer.
All right, so this next part of the story, this is where everything, and I mean everything, changes. We go from a scientific curiosity to a discovery that would completely reshape the world, all because of a few brilliantly simple experiments. So Faraday, he sets up this incredibly simple rig, just a coil of wire hooked up to a galvanometer, which is really just a fancy meter that can detect even the tiniest bit of electric current. His goal was simple. Could he make that needle move with just a magnet?
Okay, now watch what happens. First, Faraday pushes the magnet towards the coil, and bam, the needle jumps. A current is flowing. But then, and this is the crazy part, he holds the magnet perfectly still right inside the coil, and the needle drops straight back to zero. No current, nothing. So then, he pulls the magnet back out, and the needle jumps again. But get this, it jumps in the opposite direction.
So the huge takeaway here was that it had nothing to do with the magnet just being there. The secret ingredient was motion. It didn't matter if you moved the magnet or if you moved the coil. As long as one was moving relative to the other, you got a current. No motion, no current. It was that simple and that profound.
And Faraday didn't stop there. He even showed that you didn't have to physically move anything. He set up two coils next to each other. When he flicked a switch to send current through the second coil, its magnetic field would suddenly appear. And that rapid change, a field going from nothing to something, was enough to create a little blip of current in the first coil.
So Faraday had all these amazing observations, right? But in science, that's not enough. You need rules. You need a law to explain what's really going on under the hood. This is where we go from just seeing something happen to understanding the fundamental physics behind it.
To really get our heads around this, we need to talk about a concept called magnetic flux. Now, I know, it sounds super technical, but stick with me, the idea is actually pretty straightforward. Think of it like this. Imagine the magnetic field is a river, and your coil of wire is a little fishing net. The magnetic flux is basically just a way of measuring how much water or magnetic field is flowing through the opening of your net at any given moment.
And this leads us right to Faraday's masterpiece, his law of induction. He realized the key wasn't the amount of flux passing through the coil, the secret ingredient was the change in flux. The only time you create a current is when the amount of magnetic field passing through that loop is actively changing. That word, change, that's everything.
Think back to the experiment. If Faraday pushed the magnet in slowly, the flux changed slowly, and he got a tiny little current. But if he shoved it in there really fast, the flux changed rapidly, and he got a much bigger surge of current. The faster the change, the more juice you get.
But wait, there's another layer to this, a really cool twist. The current that gets created, it doesn't just flow in any old direction. Turns out, it's actually, well, it's kind of a rebel. It has a very specific purpose.
This is what we call Lenz's law, and to put it simply, nature pushes back. When you try to change the magnetic flux through a coil, the current that gets created will always flow in a direction that creates its own magnetic field to fight the change you're trying to make. It's like nature's built-in opposition.
So why does it do that? Well, it all comes down to one of the biggest rules in the entire universe. You can't get something for nothing. It's the law of conservation of energy. See, if the current helped the change instead of fighting it, you could give a magnet a tiny nudge, which would create a current that pulled the magnet in faster, creating more current, and so on. You would have a perpetual motion machine cranking out free energy forever. Lenz's law is what makes sure there's no free lunch in physics.
So we've got the science, we've got the laws, but how do we get from a twitching needle in Faraday's London lab to, well, to everything around us today? Let's connect those dots.
You know, when Faraday first showed this whole thing off, some politician supposedly asked him, well, that's all very clever, but what's the use of it? And Faraday's reply is just legendary. He understood he was onto something truly fundamental, and its potential was just like a baby's, limitless, but maybe not obvious right at that moment.
Well, let me tell you, that newborn baby grew up. We're talking about electric generators, transformers that step voltage up and down, our lights, electric trains, computers, telephones, the entire electrical grid that we all depend on every single second of the day.
A modern power plant is really just Faraday's experiment on a ridiculously huge scale. They use mechanical energy, like falling water or steam from burning coal, to spin a massive coil inside a huge magnetic field. And that constant spinning creates a constant change in magnetic flux, which in turn generates a steady stream of alternating current.
And the scale here is it's mind-blowing. A single modern power generator can crank out 500 megawatts of power. To give you some perspective, that's enough electricity to turn on 5 million 100-watt light bulbs all at the same time. Just incredible.
And that's really the bottom line here. Every single time you flip a light switch, you are tapping into a principle that was uncovered by a curious scientist moving a little bar magnet in and out of a coil of wire. That simple relationship is the invisible engine of the modern age.
It really makes you wonder, doesn't it? Faraday's discovery was once just a laboratory curiosity, something you might call useless, and it ended up powering the entire planet. So that leaves us with a pretty big question. What's the next useless, newborn baby discovery being made in a lab today that's going to grow up and change everything all over again?